Hello everyone, I'm Jiayu Zhang from Zhong Laboratory, and I'm very happy to give this talk about my work on a quantum approach for reducing communications in classical secure computations with long outputs. As the title suggests, in this work, we study how to construct quantum protocols which reduce communications in classical secure computations with long outputs. I will explain what it means. And the big message of this work is we study and discover a new type of quantum advantage in cryptography, which means our protocol achieves something that is not achievable by any classical protocols. So let's first discuss the backgrounds. So there are a lot of quantum advantages in cryptography. The most famous one is quantum key distribution, which achieves information theoretically secure communication. And this is classically impossible. So it's a very famous quantum advantage. And there are also many other types of quantum advantage in cryptography. For example, people study unclonable cryptography like quantum money and so on. And quantum crypto could help us weaken some assumptions in some cryptographic protocols. And we have position verification. And this is pretty good. And could we get something new? So to discuss our contributions, let's first discuss what is secure computations. One famous example is Yao's millionaires problem. Suppose that two millionaires want to compare who is wealthier, but they do not want to reveal how much money they have to each other. So they want to construct a cryptographic protocol between each other so that what is revealed in the end is only who is wealthier. And their amount of money could be kept secret and private. So in this problem, the input is the amount of money, XA and XB, which are private inputs from either parties. And the output is also relatively simple. It's 1, 0, or -1. And in classical cryptography, this has been studied by many works, and people have raised a lot of techniques and protocols for these problems. And we want to consider a more advanced and complicated version of this problem, which is secure computation with long outputs. Suppose that there are two servers who want to perform some secure computations on some functions, and the input is still XA and XB, which are n-bit strings. And the output could be long strings. We could denote it as YA, YB, which are n-bit strings. Here m could be big. So for this problem, we ask, what is the amount of communication needed? That is, we want to design a protocol that performs secure computations for these functions. And we not only want to achieve this task, we also want to reduce the amount of communication, which is the total size of bits in the transcripts or in the communication. By using classical techniques like FHE and succinct arguments, we could achieve communication complexity or n plus m. That is, the communication complexity only depends on the total length of the input and output. This is actually pretty non-trivial. This is already pretty non-trivial because it does not depend on the circuit evaluation time, does not depend on function evaluation time. But this is still undesirable because when the output length could be big, which means when m is big, this is still pretty long. But in classical world, we already know that this is unavoidable. By HW15, it's actually impossible to achieve poly-n communication if we only consider classical protocols. So here comes our results. In our work, we show that by using quantum techniques, by using quantum communication and computations, we could design a protocol for this problem such that the size of communication is only poly n, which is better than any classical solutions. We note that here we only achieve approximate security, which is weaker than the usual settings in classical cryptography, but we could still adapt the results in HW15 to our setting. And even with approximate security, this is still impossible classically. In summary, we have achieved a new type of quantum advantage. So we will go to the technical overview. We will first study a special case of the problem called secure function sampling, and then we will construct our protocols based on the secure function sampling protocols. So what is secure function sampling? This is a special case. This could be seen as a special case of the general secure computations. We can say that there is a public function f, which takes n-bit string to n-bit strings. So f is an polynomial time classical function. Here m could be big, and there's no private inputs. And in the end, the client gets a random x, where x is sampled during the protocol, and only server gets a corresponding output fx. And we also want the security to hold, which means to hold against the malicious servers, which means even if the server is malicious, what it could get should be normal than fx, or it is called cheating. So we want the communication complexity to be independent to the output length, and which means it should be only polycappa. So the setting is summarized on the right-hand side, and we could prove that in SFS, poly-n communication complexity is classically impossible. Roughly speaking, the proof is as follows. By adapting HW15 as follows. If we have a secure classical protocol whose communication complexity is only poly-n, this means that fx could be compressed to poly-n bits. But for some function f, like random functions, the output of f is incompressible, which means this is impossible to achieve for classical protocols. Then let's go to our construction of quantum protocols. We will not show our protocol in very detail, but we will list some ideas and techniques and give a demonstration of Tor protocol. One idea is we make use of the fact that in the quantum world, information could be deleted. This is sometimes called the Heisenberg identity principle. If you measure the state in one basis, then you lose the information in the other basis. And we will also use a problem as RSPV, remote superposition with variability, and we will use the framework results to study this problem. And finally, we will also use existing results in this paper, whose title is Succinct Classical Verification of Quantum Computation. In that work, the author gives a compiler that could reduce the server-to-client communication. So we will first construct a protocol where the client-to-server communication is poly-n, which is succinct, and then reduce the server-to-client part by this existing works. So let's give a toy protocol that demonstrates the first idea. The idea is as follows. The client, for example, two inputs, x0 and x1, and sends the superpositions 0x0 plus x1, 1x1 to the server. So the server could evaluate the state, evaluate the function of the states, and get superposition of input outputs. Then the server could perform Harman measurements on the second register, which destroys the input part. So the remaining state is 0fx0 plus some phases and 1fx1. So we could see x is deleted. The input is deleted, and what remains is only the output. And then the server could measure on a standard basis and report the first register. and the client could store the corresponding inputs, and server holds the corresponding outputs. We note that this protocol, in this toy protocol, we only consider an honest server during the protocol, which is not what we want in this problem. So what we have achieved is only very informally described as a protocol that is secure against an honest server. This is, and to achieve the disaster security, we need many more ideas. We refer to the paper for more details. And this is only for getting an intuition. Finally, we simply discuss how to construct protocols for general secure computation from the SFS protocol. We note that in SFS, X randomly sample during the protocol. And the first step is to construct a protocol that we call secure function value preparation, or SFVP. In this problem, X is can't private inputs, so the client could control it. And let's construct it. And the next step is to construct secure computations from SFVP, which will be omitted in this talk. We will need a primitive called Yao86 circuits. Yao86 circuits allows us to encode the function input in the following way. Using shared randomness, the client could first encode the function, which is called function encoding, and then it could encode the input separately, which is called input encoding. Then the security says a server which knows the encoded functions, encoded inputs. Then what it knows is no more than knowing the output of the circuits, the output of the function evaluation. So with Yao86 circuit, we could construct SFVP with succinct communication in the following way. The client and server first run an SFS protocol, which will sample the randomness using the function encoding, and the server will get the function encoding. By the property of SFS, this part only requires poly-n communication. Then the client will calculate the input encoding using the input X and the randomness it gets from the first step. And this step only uses poly-n communication also. And that's everything. Thank you very much.
Okay, thank you. Any questions?
Thanks to your nice talk. I'm curious about your protocol has a poly-n communication course, right?
Yeah.
Yeah. So I'm curious about the round of communication.
Let me think. Since I haven't really haven't really focused on reducing the round communication, so the round communication is roughly also. I think it scales with. I think the size of communication is roughly linear with the round of the communication, so it's basically asymptotically the same.
Oh, okay. Thank you.